I'd like to present Mr. Jared DeMott, who will be talking about some of the research that he's been doing with the Blue Hat Prize, talking about use after free mitigations and bypass.
All right, thanks.
So please give Mr. DeMott a warm round of applause.
All right, so I'm going to be talking about use after free mitigations and bypasses, some of the new stuff that Microsoft has done in Internet Explorer. And they're not the only browser vendor to do it, but it's just kind of the one I targeted because of a lot of reasons. So I'm just going to jump right in. I got a lot of material, so let me kind of dive right into it. As he said, I'm a security researcher. I've been doing fuzzing, code auditing, reversing, exploiting for quite a while. I teach a class on it at Black Hat, so if you want to come learn with me at Black Hat, that'd be great. Speak here, author. If you want to come hit me up and say hi later, I'm a pretty friendly guy too, I think. So, all right, so why did I really want to look at use after free bugs and what's going on with the browser and how that's being mitigated? What was my motivation there? Well, a lot of things. I have a general interest just in memory corruption in general. I have some past history doing some work in that space, and then specifically, as he said, with the Blue Hat Prize, kind of being part of some of the, I guess, community that helped pour some research into what became EMET through a Microsoft contest. So some history there, and so I was kind of interested, what are these two new protections in IE? How do they work? Does it relate to EMET in any way? Because you may have seen the research I did on EMET last year and bypassing that and stuff. So that's kind of what I wanted. So that was kind of the motivation. It doesn't really relate to EMET, by the way, is the answer to that. I'll show a slide on that later. So before I jump right into the meat, I wanted to give just a quick, background, because not everybody comes to these with the same kind of level of background in terms of memory corruption understanding and background on the problem. So if you're a memory corruption expert and you know everything about, various types of overflows and something, just tune out for 30 seconds and then tune back in once I kind of talk about understanding the problem, framing the problem really. So looking at some code real quick, we see that we're copying 100 bytes into a 50-byte buffer, setting so that, this is kind of the typical stack smash. You set up a stack frame, and there's some long overflow. And the way that worked was basically you overwrite some control data, like a return address, and then when a function returns, then you have hijacked execution, right? So that was kind of the typical thing many years ago. And the way that was originally mitigated, there's a number of ways, but one of the ways is with a stack cookie. So the compiler inserts some pseudo random number before the frame, gets going, and then before the frame, the stack frame returns, that cookie's checked, and if it's corrupted, then we think something bad happened. So this program isn't safe to continue executing in the way that it's been executing. So that's kind of, and the reason I'm kind of pointing out a few of these is I want to show this progression of kind of this tug of war, this back and forth. So the attacker has some attack, the defenders say, okay, we can stop that with this. And then the attackers kind of innovate again, right? So there's always this cycle of attacker innovation that's needed to kind of press the ball forward. Okay, so one of the things that came after that was like, okay, well, you've got these stack cookies, and that was kind of more in the RAM, the early 90s or late 90s or whatever, kind of more in the server exploitation, and the client-side exploitation kind of became popular. So this idea of a heap spray in 2007 or so was kind of all the rage. And the way that worked was basically from a client side, you as the browser are somehow coerced or tricked or whatever into browsing to a malicious web server. And the JavaScript that runs allocates a whole bunch of knobs and some shell codes. You have some big sled. And then after you've kind of set the stage for the attack, then you trigger the vulnerability. And that could be a long stack overflow, for example. And so long, in fact, that you hit the end of the space that's allocated for the stack frame. You've overwritten some structured exception handlers in the meantime, and you can redirect execution to just some random address, 0A, 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 right? It was kind of that easy at that time. And then you'd be off to the races with your attack. So that was kind of, one of the attacker innovations at that time. So defenders came back and said, well, okay, let's think about this, from what we can do from the operating system level. We can mark memory pages as non-executable, right? So memory pages should either be read and write, or read and execute, but not both. So if the heap is marked non-executable, then the shellcode can't run. So that's what Windows calls DEP, the data execution protection. So that was kind of the innovation at that time. And then along came ROP, right, this return-oriented programming. What that really is basically an issue with code reuse. So the attacker says, okay, let me sort of innovate again and think, I can't run my shell code as it is now, but there's already code in memory space. Okay, there's already all this stuff, and I can just kind of bounce through that, reuse that, such that I can change the page permissions on the current page to be executable, and then I can run my standard shell code. And we see before that, we see the so-called stack pivot taking place there, right? Because in many cases, your input might come in on the heap. So you pivot the stack pointer as your first initial vector move, and then you run your ROP chain, and then you run your standard payload. So if you sort of visualize ROP, basically each one of these green blocks is basically a gadget, a little snippet. So we start with instruction 7, we hit 8, and then we return, and then we go to the next green block. And these gadgets chained together is called a ROP chain, okay? So that's, kind of how that went. And from a defensive standpoint, it's like, okay, what can we do to stop the ROP? One of the things we can do is randomize the base address of the modules, right? So the attackers need to know where modules live in memory such that they can chain all these gadgets together. And if they don't know the base address of code modules, then they can't create this so-called ROP chain. So DEP and ASLR together are pretty effective if they both work perfect. Unfortunately, that hasn't been the case, right? So ASLR has been challenging to get right. And there's a lot of reasons for that. At first, third-party modules were slow to adopt, so you had a bunch of existing DLLs that weren't going to get recompiled right away. They were already something that was packaged inside of Java or whatever it was. So you had existing third-party modules that didn't opt into these new protections, right, that needed to be. And then so over time that got fixed, and then it came to be that attackers said, well, okay, the DLLs are starting to go away, but there's these shared pieces of memory. So even though all the code modules are randomized, there's these places in memory that are static and have a pointer or something that we can kind of leverage to still kick off our ROP chain in some meaningful way. And then as vendors have started correcting that. Still, we see that ASLR is hard to get perfect. There's a patch that just came out a couple months ago that resolved some ASLR issues in IE. So we still see that this idea of getting ASLR perfect has been kind of an ongoing challenge, even though the ball's moving forward in a positive way from a defensive standpoint. So along came, some of the research I talked about with the contest and EMET and all this. And basically the idea with EMET is there something else we can layer on top of ASLR and DEP that we can put on existing apps or older apps that maybe didn't opt into ASLR and DEP or other applications that just have a lot of vulnerabilities, but we still really want to mitigate ROP or whatever. There's something else we can kind of add on to that. And EMET was kind of the attempt to do that. It's got 12 mitigations, and 5 of them are specifically targeted towards stopping ROP. And I won't go through each one of them. But basically, one of the ways that I showed last year that you could bypass EMET, even though EMET was good, it wasn't perfect, and none of these are, and that's kind of the ongoing theme that we see, that it's a lot of these things that come to be, they're good, but they're not perfect. And there's usually where there's kind of a will, there's a way. There's some innovation you can come up with. So one of the real simple innovations that I used to bypass one of the protections that EMET called the stack pivot protection was basically just making sure that the stack pointer was on the stack at the time of a critical API check. So the way EMET worked real briefly was basically every time critical APIs like virtual protect or some function call takes place, they basically do some check and go, let me check and see if all these things are in place. Is the stack pointer on the stack? Are they trying to change permissions of a page on the stack? Are they trying to do this, that, the other thing? If so, then I think a ROP attack is taking place, and I'm going to cancel the execution of this program and say that it's unsafe to continue. So if you assume in many cases like it does your malicious input, your ROP chain comes in on the heap, basically all I did for my innovation was just copy the whole ROP chain to the stack and then do call the critical API, and it'll check to see if the stack pointer's on the stack, which it is, because it still isn't, it needs to be there and it is there. So there's some simple ways basically to bypass that. So long story short, you can go and read about that on labs.birmingham.com if you want to, but ROP lives on for a number of reasons. And one of the reasons that it lives on is because of this vector called use after free. And that this bug has been a real pain for vendors of various types, particularly browser vendors, right? Because browsers are very complex. The management of objects, the life cycle of these objects, they come and go all the time. It's very complicated to manage their life cycle. So use after freeze has been a big problem. And so my last slide in terms of the background or kind of the setting the stage of this problem was this. I wanted to think about, if I'm going to stop an attack, what's the best place to do that? Is it in the code? Is it by choosing a safer language? And the answer is basically yes and yes. So the simpler and the lower level your fix, the better it sort of is, the cheaper it is, right? So if you just don't use C, just use like C# or something, that would be better. You wouldn't have stack buffer overflows, but it's not practical in every case, right? You need C for kernels and heavyweight browsers and things like that. So there's a reality that moves you forward, say, well, I can't do that, but maybe I can use smart pointers, and I'll talk about that real quick. That helps manage the life cycle of the objects inside the browser. So that's a good choice. And then ASLR and DEP are a good choice. Those are low-level operating system mitigations that have made a big difference. They're not perfect, but they've helped. And then as you move up this stack, you find that basically the higher up the stack you get, the worse it is, so to speak, to try to stop the attack at that point. Like with EMET, I call it a medium level protection because basically it's not high level like AV, but it's not low level like ASLR and DEP. The attack has basically already started. The attacker has a toehold in the sense that they've started running their ROP chain, and you're going to try to stop it at critical points by noticing bad things in APIs. And that's not really the best place to stop an attack, right? Once somebody's already kind of got a toe in the door, you're going to slam it shut on them. Maybe that'll work, maybe it won't. And the worst place to try to stop an attack is like at the AV level, right? After malicious code is running on my host, it's taking complete control of my host, I'm going to notice that and mitigate it based on my AV, right? And I see a few people smile and chuckle because that's kind of the worst place to do that, right? So maybe there's some better architectural technology, and I could talk about the things that we're doing at Bromium or something, but that's not the point of the talk. I want to keep going with what I have for you today. So that's kind of the background. That's setting the stage on understanding the problem. Okay, so these two new defenses that Microsoft created are called isolated heap and deferred free. And they're meant to mitigate this problem of use after free, which we see based on Operation Snowman and Operation Clandestine Fox, and I love all these operation names because they're so awesome sounding. But the point is, there's been a big problem for a couple years now, really, with this use after free bug, and all the main sort of like memory corruption O-days that have hit the streets have been use after free bugs. So they recognize internally that, hey, we got to do something more. We got to do something more than ASLR and DEP, more than EMET. We need something inside of the browser itself, some process level protection that's going to help mitigate this. So how does a use after free really work if you're not familiar with that type of bug? In a real quick nutshell, basically some data structure in memory, which in C++ we call an object, gets allocated. And then for whatever reason, the life cycle of that object isn't properly managed, and that object is freed, but the application doesn't realize it's been freed. So you have what's called a dangling pointer, or a use after free. So you got a pointer that's kind of dangling some memory that it thinks is still alive, but it's kind of gone. But the attacker knows that and manages, usually in the client-side attack, through JavaScript, you allocate some JavaScript string or something of the exact size of whatever was gone. And the allocator wants to do the right thing and keep memory from becoming fragmented, just like you remember defragmenting your hard drive or whatever. There was these holes right from files, and you want to defragment it so you have one big space, all this stuff. It's the same kind of thing with an allocator. The allocator says, hey, you know, a 40 hex byte thing just went away, and I see somebody allocating a 40 hex byte thing right now. Boom, stick it right in that same hole, right? It makes sense. And so because of that, the way the allocator works, the attacker can, generally speaking, easily get their allocation put at that place if they have a way to do that. And then the application, which then uses the dangling pointer, tries to call method B on object A, not knowing that things got sort of, you know, changed under the hood, and that allows one of the three perimeters that you need to successfully run a memory corruption attack, a read, write, or an execute, right? So you're able to either read something out of memory space to figure out where the base address of the DLL is, or you're able to write something, change some control structure, and then hijack execution based on one of those three perimeters, or all three, generally speaking. So again, why do UaFs happen? Like, how do these things even get into the code base? As a vendor writing code, why do these show up in my code base? Again, it's because of the complexity of the code base, the difficulty in managing complex objects lifecycle. Any application that's actively being written or worked on in C and C++ today is very complex, right? Nobody's writing simple web apps in C and C++, or if they are, they're an idiot, right? They shouldn't be. It ought to be written in .NET or something else. Anything that's being written in C++ is because it has to be, because it's heavyweight, it's intense, it needs to be really fast. So it's a kernel, it's an operating system, it's a hypervisor, it's a browser, it's something like that, with tons of complexities and objects and event handlers and all this kind of stuff in it. So that's kind of why they show up. And one of the things you can really do that's kind of the best thing to start is, as far as mitigating these out of your code, is to use smart pointers instead of what's called a naked pointer or a bare pointer or a bare naked pointer or a native pointer. Basically just a pointer where you manage the life cycle. Like, don't do that unless you absolutely have to. So basically in the past, what you do, I don't know if you can read the code. I hope you guys have good eyes because the code may be a little small up there. But basically, you allocate an object, you say new, my object, and then you do a pointer, do something in that object, and then you delete the pointer when you're done. That's kind of the quick and dirty life cycle of an object, right? The problem being, if inside a do something, some exception triggers, and the object is already freed, you come back and try to free an object which is already freed, you're calling a pointer, the delete pointer method, on an object which is already gone, which is basically a use after free. So if you use a smart pointer, you define a smart pointer on that object, and then you just do something, and then if that object goes away, that's fine. You never have to worry about freeing it later. It gets freed by itself based on the reference count. So when the reference count of that object goes to 0, then the object goes away. It's kind of an automatic collection of objects through smart pointers. So that's kind of the ideal way to code. But even so, there's a few problems with that. Certain Windows APIs require native pointers, so that's bad. So you can't use smart pointers throughout your whole code base. On top of that, keep in mind that the reference count is just basically an object which has a pointer to the real object which lives on the heap, so you could potentially corrupt the reference count itself. So there's all kinds of ways and places where even if you're doing the right thing in your code base, you could still end up with use after free vulnerabilities, which is why Microsoft wanted to do more. They knew that smart pointers alone wasn't enough. They weren't going to weed them all out with code analysis and code reviews and stuff like that, so they needed more. And that's where these two new protections come in. So basically, isolated heap, they're real simple to understand and to think about how they work. The isolated heap basically just says, in the past, every object that I allocated went to the default process heap. But now, I'm going to make a separate heap, and certain things are going to go to the isolated heap, and all the rest will still go to the default process heap. So it's kind of, I have kind of an ongoing analogy I'll use throughout the talk of basically school children on the playground. So good kids over here, naughty kids over here, sort of thing. And the naughty kids would basically be the objects created that potentially are under the influence of an attacker, like JavaScript strings created by the web server, whatever, stuff that isn't native to the internals of the browser. So the internal IE objects go on the isolated heap. Untrusted stuff, objects should go to the default process heap. So if you think about that in terms of how can I bypass this protection, which is the way my mind thinks about everything, first, you can tell that right off the bat, that's a hard thing to do, right? Like, what school teacher can go out on the playground and go, well, these are the good kids and these are the bad kids, right? It's a hard problem to solve because maybe some are a little of both depending on the time of day, right? Or something like, it's not easy to separate the two groups cleanly. And it's the same with the objects, right? It may not be clear which objects should exist on which heap. There may be some that could go on either. So there could be some problems there, right? Right off the bat, we sort of have that gut feeling. Even without doing any research, we sort of think maybe that's good. It probably helps, but it's probably not perfect, right? And that's basically what it boils down to in the end, to kind of cut to the chase. It helps, but it's not perfect. And so how do you create a new heap? If you're writing code and you want to implement this protection, which I recommend you do if you have a problem with use after freeze in your code base, it's because it's super simple to implement this protection. You just call heap create. It's just a Windows API, and you just create another heap, and you can just allocate certain objects to one and certain objects to the default. So it doesn't cost you anything to add this protection, right? It's like a simple design decision that makes sense. More specifically, which objects go to the isolated heap? Basically, the DOM type objects, the C element, SVG element, C markup, C tree node. So if you're not familiar with the internals of IE, this may not mean anything to you, but if you're familiar with IE's internals, you might recognize some of those object names. And what I did is I wrote a Python script that basically parses the MS-HTML .dll, IDB, the IDA Pro representation of that DLL, to basically find every allocation, its size, its name, and which heap it goes to. And it's really easy to figure that out statically. So, and I'm going to release that code actually right after this talk. I'm going to go back to my room and put out the blog article on labs.bromium.com. I'm going to put out the code and the slides and some more details about this talk. So if you want the Python code, you can go find it there. And basically, it's really easy to find that information. If you look at a given object in IDA Pro, like this is the C text area object, which is 70 hex, and this was before the protection, so before June of 2014, and then after, like June or July of 2014, you see that the only thing that changed about this particular object is that the heap handle is now global handle isolate heap. So this object goes to the other heap, basically. So it's not hard to figure out which heap they go to in IDA Pro. It's really straightforward. Okay, so that's the isolated heap. The other protection, knowing that this first protection isn't going to be perfect, right? Just like DEP isn't so great without ASLR and ASLR isn't so great without DEP, you kind of need both. It's the same thing with these two protections. They sort of need and depend on each other because isolated heap alone isn't perfect. So they had this other idea of delayed free. And to go back to my sort of naughty kid analogy on the playground, suppose what the naughty kid really wants to do is cut one of the kids in line. Because if you ever watched second graders in line or whatever, that's what they really want to do. They want to cut the other child in front of them, right, and get ahead in line. So assuming that one child has to leave the line to, I don't know, go use the restroom or something, the other child, the naughty child, can just come right in and take their place in line. That's kind of generally how a use after free works, right? You can take that space in memory that was just freed up really quickly. But with delayed free, we're basically saying, hey, the teacher's going to watch that spot for a little while. I'm going to keep an eye on that. Hey, this guy's gone, but I haven't actually freed this spot in line. I'm kind of keeping an eye on this spot. And that's basically, from a real high level, how delayed free works. It just delays the actual freeing. So when you, instead of calling heap free on an object, they change the heap free function to a function called protected free. And protected free basically puts that pointer to that object on a list of things to be freed at some point, but not right now. Okay, and if you think about, okay, and so the first thing I'm doing, as always, when I think about this is, how can I bypass this? What's the first thing that comes to mind? And the first thing that comes to mind is that teacher can't watch that spot in line forever, right? Because she's got other responsibilities on the playground. She's got to go handle this or handle that, right? You're going to end up with some resource issue if you watch that spot forever. You basically end up with a memory leak, right? If you hold all memory forever and you never release anything. So at some point, you really have to release that. So to make it a little more concrete, what gets created is this data structure in memory called a C memory protector. And this is like a per thread memory structure that's created. So every thread has this own sort of, has this delayed free protection enabled on it. And inside of the structure, the first bit is what's called the blocks array. And as part of that, we have a pointer to the list of blocks to be freed at some point. And the address, the first two bits of the address are special in that list, basically. The 0 bit indicates whether or not that address is marked, and if it's marked, it means it can't be freed. It's not ready to be freed yet. And bit 1, or the second bit in that address, indicates whether it came from the isolated heap or not. If it's set, then it came from the isolated heap. And that's just kind of like housekeeping used to figure out how to properly free it when the time comes to really free it. And there's also things like the total size of the list, the count of the list, the max count, is it sorted or not? It keeps it sorted to more easily look through it when it comes time to free things. And there's this is force mark and reclaim bit, and there's also some information about the current stack frame, because what happens is when the stack frame of all the things that were just happening in this thread unwinds to where it started, everything gets freed regardless. There's like a catch-all cleanup routine that has to happen at some point, so you don't end up in a memory leak situation. So what happens when you call this protected free, basically? First thing it does, before it actually even puts the new chunk on the list, it basically checks to see if it needs to deal with the list as it is first. So it checks, is the list of size 100K or not? And so that's kind of the magic number in terms of, if you get the list to 100K, it'll call this mark and reclaim operation. And if it is, then mark and reclaim will run. Otherwise, it basically just sticks the current chunk onto the list, updates the size and the number of elements and stuff like that. Okay, so when the mark and reclaim runs, basically what it does is it checks the current block and says, are there any pointers to this block on the stack anywhere? And if there are, I'm going to mark it and say this guy's not ready to be freed, because I think that somebody still has a reference to it. There could be a dangling pointer kind of hanging onto this guy. And that's probably the most effective part of either of these protections, is that piece right there. that piece that says, I'm not ready to free this because I think there's still a pointer that exists. It actually searches the stack every time this operation gets called and checks to see if there's pointers to it. And if there are, it won't free it yet. So that's good. That's actually like the best part of this implementation, I think. And if there's not, then it'll free it, basically. So if it is, it'll mark it and say no, and then all the unmarked blocks will basically be freed. And then, of course, there's this unconditional thing that happens every so often as well. So even if there are still marked frames, if you get to a certain point in the call stack, which basically is a full unwind of that thread, it says, I got to unrelease everything anyway. So there's this idea, and really to cut to the chase, the kind of the results of my evaluation of these is that long-lived dangling pointers are a problem for this protection, because it does between the two, isolated heap and delayed free, it does a really good job of stopping a lot of the use after free bugs that are out there, all the sort of short-lived use after free bugs. But any long-lived use after free bugs where you have just a heap reference to that handle that lives beyond the current call stack, you could still have a dangling pointer that's going to trigger a use after free bug in that situation. So that's kind of the really the meat of the of this section of the talk, the evaluating the solution. How effective are these solutions? I basically just cut to the chase and told you. But let me walk through that anyway and kind of support that with a little bit of the work that went into that. So I chose 4 bugs, one from 2012, one from 2013, and 2 from last year to kind of dig into that. And the reason I only chose 4 instead of like 10 or 20 or something to kind of do the research on it is because it's a pretty time-consuming thing, right? Understanding and playing with even one use after free bug is hard. It takes a long time to understand what object am I dealing with, what's the life cycle, why did it get prematurely freed, how can I fill that spot? Like, it's kind of hard to begin with. So doing the research on more than one of those is sort of a pain in the tail. So I just chose 4, and I think it was good enough for what I did. And basically, I kind of kept track of some information, like what is the object in question here? Where was it originally allocated? Where does the fault take place? What's the size of the object in question? And what heap was it on? And what heap is it on after the 2 new protections were put in place? And interestingly enough, 2 of the 4 stayed on the default heap when I expected all 4 to go to the isolated heap, right? Because they were objects that obviously had some prior past naughty history with use after freeze. So that sort of supports my theory to start out with it. It's hard for the teacher on the playground to figure out which object should go to which heap, right? That's sort of a hard problem because there's so many objects in complex code base. It's very time consuming for developers to go back through and reevaluate the life of every object. Say, this object I think will only ever be useful on this heap, and this object I think is probably only like, it's sort of a hard thing to do. And so that I think is not the best part of the protection, right? So I think regardless of what heap you end up on, I think you can probably find an object that'll be useful in terms of replacing the original with something else that's helpful in terms of an attack. So I think the heap isolation it's cheap and easy to implement, and it kind of helps, but I think it's not so great as the delayed free. I think it's more effective. Yeah, I think I said most of that actually. So in terms of a bypass, I think I said most of that actually as well. So let me just move into this slide. So what this slide is showing is basically the first part of a mark and reclaim operation. In other words, building the list up to the point where it's 100K in size, 100 kilobytes waiting to be freed. That's really easy. In JavaScript, just allocate and free a bunch of objects until you get to 100K. So that's like a no-brainer in terms of bypass, right? There's nothing you really have to do. Maybe just add like one function to your attack, right? And you can do that. The more effective piece of that is, are there still pointers on the stack that point to the object? And that really, like I said, that's the crux of the protection. That's the only piece that's really effective at all, in my opinion. That really does much to slow you down, and that's helpful. Are there other ways besides this long-lived dangling pointer idea that could be used to bypass these 2 protections? Certainly there are. I had other esoteric ideas like, well, this list of things waiting to be freed lives on the heap somewhere, so if you could corrupt that, or you could corrupt, you could change the fact, if you can change things on the stack, you could erase pointers that are on the stack that are still there to make sure that the mark and reclaim frees the output. But it didn't really make sense to go down any of those roads, because if you can do any of that, you probably don't need the use after free bug anyway if you can already corrupt the stack or the heap or something else. So it's kind of like I really wanted to stick with what I was trying to stick with, which was trying to figure out stuff about these 2 protections more specifically. Other things, if you could force like certain APIs to fail, like the APIs that check to see if the protection's even enabled, because you can disable these two protections through an API. So that, but I didn't go down any of those roads. I didn't feel like they would be successful. I felt like the only reasonable way to bypass these protections is with this long-lived heap reference idea. So let me briefly dig into each one of these four, and it'll be very brief. Like I said, I'm going to put my slides up on our blog after this if you want to kind of go through them slower, because I could spend all day trying to explain each one of these four use after frees, because they're pretty complicated in general, I think. So in a nutshell, this bug from 2012 uses the CMSHML-ED object, is the object that's wrongly freed. And basically, you get it allocated by calling this exec command function, and then there's some event handler. And this is a common theme. You'll see this a lot in JavaScript, right? Like if you're looking for use after free bugs in the browser, and you're doing it by trying to manipulate JavaScript, think about event handlers, right? Because that's the place where you can get stuff kind of set up and allocated and orchestrated in a certain way, and then you can trigger some odd event that the browser, there's this disconnect between what the browser thinks is happening and what's happening in the JavaScript world. Control kind of transfers back and forth between the two in the browser world, right? The browser's running native code. You have influence over JavaScript, which is kind of running over here from the web server standpoint. If you can trigger some event and something gets freed, and then when that event returns, that object tries to be used again, that's how I would say like 80% of the use after free bugs in browsers are found, by sort of manipulating events and stuff like that. So, and that's exactly what happens here. You're able to trigger some event and then use the document.write command, which basically destroys the current DOM tree, and then which releases that object, and then you come back and you try to reuse the object, and you have your use after free. So what is the, I don't know if you can really read that or not very well, but what is a snippet of the proof of concept, the malicious hosted web code look like that triggers a bug like this? Basically, you have some function called onload. So when the web page loads, you run function B. And function B sets up the object with this document.exec command. And then it calls select all, which triggers an event handler, which calls function A. And in function A, you do document.write, which destroys one of the current objects that are sort of needed. And then before you use it, you do some stuff like force the free and spray, which fills that space with attacker controlled data. And all my attacker controlled data is just a bunch of Unicode string 99999. So in this case, it's not a working exploit. It's just like a proof of concept to show the idea of a use after free and how you can refill that space, which was wrongly freed, and have it crash at like 0. It'd be like 3900, 3900, 3900. You'll see that in memory, right? If it like crashes on a pointer that looks like that, we know that we were able to fill that space with our own stuff. And then we trigger the bug. Okay, so before I show you the low-level dump inside the WinDebug debugger that's showing that, how do you think about these in general in terms of debugging use after freeze? What are kind of like, if you think you're dealing with a use after free and you need to like, write a working exploit or trying to figure out how it works or whatever, what are kind of like the general high-level steps you take? And the first one is basically, obviously getting familiar with IDA-Pro and WinDebug, right? Those two tools are a must. You need to understand your debugger and your disassembler. And so you figure out, you get it to crash in the first place, and then you kind of go back and forth between the static and the dynamic, and you figure out, well, what object am I really working with here? What's its name? What's its size? Can I figure out, where it's allocated, where it's free? That's the kind of stuff you're going to be trying to figure out. And then, of course, once you understand the object, then where was it freed wrongly? And what you do before you run the iExplore in WinDebug is you use gflags to enable plus HPA and plus UST, which are the debug heap and the user stack trace. And then that basically gives you extra information about the allocation, right? So then you can type bang heap -p-a in the address, and you can figure out, it'll give you a stack tracer. Here's are all the calls that led to it being freed. Okay? And then once you know where it was freed, well, then you go back and go, well, where was it allocated in the first place? Okay, and so you can basically rerun with a breakpoint just before it's freed and run that same bang heap -p-a address command, and it'll give you the trace of where it was allocated rather than where it was freed if it hasn't been freed yet. Okay, so basically you're kind of keeping an eye on that chunk, that allocation, before and after. And then where was it used again is the final step. So you can just run it again or whatever and look at where it crashes and look at the actual stack trace of where it dies at that point. And basically you try to do like a set intersection of those 3 call stacks. You take all 3 call stacks, put them next to each other, and look at what's common across, draw a line basically across the 3 and figure out what's common. Where was it allocated? Where was it freed? They're all common to like this point, and then you can kind of figure out the differences beyond that to figure out sort of what went wrong in terms of the event handler. This is where it got freed, and this is where it's used again later when it comes back from that or whatever. You can kind of piece that together. So it's kind of it's basically a complex reverse engineering task. And that's one of the things that makes use after freeze kind of difficult for the vendor to deal with and fix. And one of the reasons they still exist in code base is developers sort of have the same problem. Normally developers kind of have a leg up on reverse engineering attackers, right? Because they have the actual source code. So you think, well, they've got the source, so they've got it a lot easier in terms of figuring out what's happening. But with use after freeze, it doesn't help that much having the actual source code because it's still hard to figure out, okay, I see that it dies at this line of code, but why? You know, you still have to go through that same process of figuring, oh, it was allocated over here, and then it got freed in this routine, which I had no idea could even get called from this routine, and then it finally, so it's kind of the same sort of problem, basically, which makes it hard to fix and repair and kind of deal with those bugs from a development standpoint. Okay, so looking at, maybe, again, it may be a little hard to see, so I'll just kind of, talk you through what you're seeing in brief. But basically what I'm showing you is, in the original case of the bug, without the protection, we can see that the replacement worked. We see a bunch of like 3900, 3900s at the very bottom. And so I was able to, refill the original object space with memory data that the attacker controls, and then it stops. And at some point, that's clear that we influence the execution from that point forward, based on how we were able to replace the data at that point. But one of the things we notice is that there is pointers to this object on the stack, okay? And why that's important, again, is because of the delayed free thing. So once the delayed free patch is put in place, this same attack wouldn't work. What you would see is basically, instead of that memory space being filled with 3900, 3900, our stuff, it's just filled with all zeros. Because what happens as part of that, when you put chunks on this list to later be freed, it also, I don't know if I mentioned it, but it also zeroes out that memory area. So it zeroes it out, puts it on a list. So you have this area of memory that's full of nulls or zeros, but it hasn't actually been freed yet. So we can't put our stuff there. We can't get a new object allocated at that spot until the actual free takes place. So delayed free sort of is an effective mitigation. At least in this case, it seems to really make a difference. And the same thing with this next object, or this next bug, basically without going into all the nitty-gritty and details. We see the same kind of thing taking place, that originally, without the protection, we're able to successfully do the UaF and reclaim that area with our own data. In this case, I used like 11223344. We see that. I don't know if you can see that or not in the memory space, and it's using that as a pointer. But for the same reason, that area is just full of zeros, and we're not able to reclaim it once the patch or the protection is put in place. So it seemed to help against 2 of the 4. For the other 2, not quite as much. So with this use after free involved the C element object. And in this case, this is the original case. It worked, and we were able to reclaim that memory. And also, it looks promising in the sense that when I did a search for that pointer across the whole memory space, I don't see any references to that pointer on the stack. Okay, and because of that, we can reclaim that area. But one of the things I wanted to point out with this one, this third one, it was one of the ones that used to be allocated to the default heap, which made attacking it really easy because you could just use strings inside of JavaScript to fill that same area. But now this one's on the isolated heap. And so I have to visit that question of, okay, well, so this one goes to the isolated heap. Can I find allocations or other objects that also go to the isolated heap that are helpful? Because I know that strings don't go to the isolated heap. They still go to the default heap. So I can't use the same old technique I've always used. So like my existing attacks, basically, or my existing method of filling that space is broken now. So I have to kind of innovate a little bit, which turns out to be not that hard to innovate. There are certainly other objects that go to the isolated heap that are still useful for doing the same kind of replacement. And so I used this Python script I mentioned earlier, and I found some different objects, all of which are the same size that could potentially be useful. Basically, it takes a little work, though, because you have to figure out, how do I get this object allocated? Can I control all of the contents in it, starting with, at what byte offset, blah, 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 blah. There's all this sort of RE exploit development work that goes into understanding how useful these are. But one of the questions I had was, does the replacement object actually have to be the exact same size? In other words, if it was 70 hex before, does the one I replace it with still have to be exactly 70 hex? Or can I broaden my options of objects? Can it be a different size? And the answer is yes, it can. So I found or noticed this blog by Keen Team that they do some exploit development stuff, and they had posted a blog basically on this topic as well, as it relates to kind of bypassing these protections. So what they'd done is they had played with this MS14056 bug, and I don't know if you can read the JavaScript code, but basically it sets up some objects and some elements, and it sets up an event listener, and then it wrongly frees or creates the situation where you have a dangling pointer with this object inner HTML equals object inner HTML. That's basically where the dangling pointer gets created, and then they trigger the use again with this document.write is where the use after free kind of gets triggered. So basically, between those last two lines of JavaScript is where you have to insert more to kind of get your attack working, where you would do like your spray or your replacement or your force free or whatever like goodies you want to add to that to kind of upgrade this such that it works against these two protections. That's kind of where you have to add the goodness, so to speak. And if you look at this bug, the way that it crashes without the protections, you see that it looks promising. Again, I don't know if you can read it at the very bottom, but I'm doing a search for the object pointer in question, and I see that there's no results returned, so there's no place on the stack anyway that's holding a reference to that. And in fact, this particular bug was able to be upgraded such that we could bypass both the delayed free and the isolated heap. And I don't know if you can see it, but you see some 41, 41, 41, 41 stuff in memory. Basically, those are, are showing, proof of concept showing that arbitrary data of our choice could replace the vtable pointer of the original object. So it works, so the bypass is good. So how does it actually work, though? Basically, like I said before, no real trickery is sort of needed to bypass the two, in the sense that a little bit of trickery maybe, but basically you're just naturally waiting for this object to get freed because it's long-lived. So you don't have to kind of force this delayed free to happen in any kind of particular way. You just wait until that naturally happens. So you have a long-lived reference. So that kind of is bypassable. And you can see the call stack. Basically, there's a protected free called, and then the actual heap free is later called in that same stack frame of this object's life. And as far as defeating the isolated heap, what they did was, instead of using a JavaScript string, which was kind of the way to do that in the past to replace the object, they used the C area element object. And the interesting thing about it is it answers my question from before, is can the object that we use to replace the original be of a different size? And in this case it is. The original, the C title element, was 40 hex, and the new object is 64 hex. The C area element is the one that gets used, and there's some data members of that object. You see the area I dot coordinates equals some decimal number, which is 41, 41, 41, 41 in hex. That's what actually gets used to replace the vtable of the isolated, the C title element object. So how is that possible? That one is a different size, we still used it to replace one that was of a smaller size, and that was really what I wanted to understand. Is that possible? And the way it's done really is what's called coalescing, and it kind of made me laugh. When I saw this and realized this, it's kind of like, geez, we've been talking about coalescing for like 15 years in the exploit development world. I remember like 15 years ago talking about when writing heap overflows was possible, there weren't much protections in the way of the heap linkage. When heap chunks got unlinked, based on the way coalescing worked, you could change the pointers of those things through coalescing. So it's just kind of interesting, non-related, but interesting that coalescing has been sort of helpful to attackers for like at least a decade and a half that I can think of. It's kind of interesting. Basically what you do is you allocate a few different objects of the same size of these hex 40 objects. You do one before and after the one that actually gets dangling, the dangling pointer. And after the dangling pointer situation is created, you force those smaller chunks to coalesce into a bigger chunk, and then you allocate an object of a bigger size over top of that. And that way you don't have to have an exact offset either. You can have data members that are of a further offset in the object that you use to replace it in the object that was of smaller size. So it gives you more flexibility in terms of how you overwrite the V table as well. So it's sort of like doubly good. So that's kind of the almost final portion of the presentation, basically showing explaining how the protections work and showing how to bypass them, at least one scenario. So in summary, I talked about use after freeze today. I talked about how they worked and how to potentially mitigate them through some new defensive techniques that browser vendors have been pouring some research and some expertise into. And I talked about how they're good, they're not bad. The point of this talk isn't to say, hey, these things were terrible, they didn't work at all. They actually worked fairly well. But like many of these low-level mitigations, none of them seem to be perfect. There always tends to be this cycle of you create a new defense and I'll innovate in some way to sort of get around that, right? So we see that pattern continuing. We expect that pattern to continue. So is there anything else that Microsoft could do to deal with this, and specifically this case of the long-lived dangling pointers? Is there something they could do to kind of tweak this protection a little bit such that it's effective against that as well? And the answer is probably one of the things that comes to me off the top of my head is not so much making the delayed free longer in its delay, because eventually you're going to have a resource constraint, right? Like you can't hold it forever. So that may not be the answer. But there's this other thing that's totally different called control flow integrity, which I think is going to be one of the things in the future that we'll see really help stop or mitigate some of these sorts of memory corruption bugs. So expect to see some more on control flow integrity in the future. And again, pointing out the obvious, I was just talking about UaFs. There's other types of memory corruption bugs that are still alive and kicking. There were some examples from this past year, the unicorn bug and some of these other ones that had funny names that are kind of non-related to this that still work, that aren't at all related to this. So I'm just kind of pointing out the obvious there, that there's other things still taking place. If you have an application that is potentially vulnerable to UaFs, should you implement these protections? And the answer is, yeah, sure, why not? They're not terribly expensive, they're not terribly hard to implement, and they seem to help a fair bit. Why wouldn't you also put those in your application? So I would recommend that, I guess. And in terms of trends and predictions for the future, the next 5 years in security or whatever, do we expect to see memory corruption bugs go away and be fully mitigated, or will they live on? My prediction is basically just a historic look at what we've seen. We see that every 5 or 10 years, we see this cyclic pattern where attackers have this, they can do these complicated use after free attacks or whatever, and then some mitigations will come along that make that hard, and so you'll see that kind of go away for a couple years, and then the attackers will sort of go back to just like calling people and asking for their user and pass or whatever, some sort of low-tech sort of attack, right? And then they'll innovate, there'll be some innovation in attack technology, right? And then you'll see more complicated memory corruption bugs again, and like that pattern seems to go up and down like every 5 years or so as far as what actually is being seen from like the enterprise standpoint. So I expect to see that same sort of trend continue. I don't really see any reason why that would change. One of the things that's interesting is that we are seeing innovation from a defensive standpoint react faster. Like, so for example, the Morris worm used the stack buffer overflow in 1988, and it wasn't until Visual Studio 2002 that we saw the stack cookie, right? So that's like 14-year delay between problem and, potential problem solve, which it didn't really solve the problem, but it helped, right? Where with UaFs, we see them sort of turning up around 2008, and in 2014 we see these two UaF protections in IE, so we see a 6-year delay. So we see that getting faster, and that probably happens for a lot of reasons, partly because if attackers are moving faster and innovating quicker, defenders need to do the same. But there's still always going to be this delay, right? And I call it quote unquote business justification, right? So even though we saw a couple of use after freeze in 2008, maybe a little bit of an issue here and there, it wasn't until 2011 until sort of the pain threshold, the pain point really got kind of crossed, where the vendor says, hey, this is starting to hurt. We need to do something about this, right? So there's always basically some level of risk, some threshold. In security, it's not about 100%, it's about mitigating risk, right? So it's about when does the threshold cross to the point where I feel like I need to do something about this. So anyway, my time is up, exactly 50 minutes on the dot. Thank you very much. Any questions for me? Yeah, go ahead.
Yeah, I'm not a security guy, like expert.
Okay.
In the programming realm. So when you're saying delayed free, is that like it's being, the memory that previously been allocated is being nullified, and as such, you don't want to free that up for somebody else to utilize so that they can't get bad data? And also the other thing is like, how is it that people are getting this memory? Like, could it be like a simple mem set would suffice for the memory that they had allocated to nullify the memory for, like, okay, now I've got a pointer to an address space, but that memory is nullified now, such that one needs to be used.
So the question was some more details around how delayed free actually works. Delayed free works by not releasing the memory actually to the allocator right away, right? So even though it's nullified with like a memset 0, like you said, what was there is nulled out, but it's not actually freed up so that somebody else can take that space in memory. It hasn't actually been freed yet. That's basically kind of in a nutshell how that works. So, any other questions? Okay, I think, oh, one right here, go ahead.
So the answer to the delayed, or the long-lived pointers was just to wait it out. But you also said it's technically free, doesn't mark or use memory until their reference count reaches 0. So I missed the part that just waiting it out, it would ever actually be used. It seems like the technical free still hasn't protected as long as the reference.
So the question is more about protected free and how it works in relation to waiting it out. The problem with waiting it out is two things, right? So the reference count hits 0, you free an object, but you're saying, you know, this object is gone, it's free, but I don't want to free it just yet because I don't want to free it up to actually be useful to somebody else yet. I'm going to hold it longer than what normally would happen in an allocator. Okay, so then at some point you have to release it, otherwise you end up with a memory leak problem. You can't hold everything forever. At some point you have to release and free memory. And that's where the long-lived issue comes in, is that at some point they have to release it and you just wait until whatever point that is to kind of trigger the attack.
What is that point? Why does it release it?
It releases it eventually when it's per thread protection. When that thread, eventually the call stack of that thread finally unwinds to wherever it started, then everything has to be released. It's just kind of, that's just the threshold they set. So maybe you could tune that to be something else, but at some point you still have to release it. So.